Hi everyone, welcome back to my channel. So in this video, we're going to talk about something that's called as Azure quantum computing. So we have quantum computing also there in Azure. So we'll be talking about it. I'll be talking about it a little. We have some sessions. I wanted to start with how you can learn about Katas. Katas is a learning platform or a coding platform uh, on which, or a coding language using which we would be doing the uh, quantum computing or quantum related programming in Azure. Okay, so if we start about it, I've mentioned a little bit about it in my blog, so feel free to look at it if you want to start reading about it. I started it like a couple of months back, and I'm still working on it. So I wanted to also share this, read this along with you. So let's say, welcome to Quantum Katas, the Japanese word for form, a pattern of learning and practicing your skill. Okay, so a self-paced AI assistant learning. So you can also learn about Kata and other things from here. This is like a co-pilot which can help you answer a lot of your questions. So programming language in quantum or Azure quantum is actually Q sharp. So this is focused on quantum computing and programming, and this tutorial is basically how you can do interactive with theories about hands-on practices with quantum katas a little. So I mark this as complete. I go to next, and in the next we understand what a qubit is. Qubit is actually the so we have zeros and ones in our in our basic systems, in our logical systems, but quantum computers don't work with that logic. They work with something that's called as qubits. Qubits is a state where a bit can be 0 and 1 at the same time. That's what the whole thing is. So the first code, or the first piece of code that I would be writing, is an exercise that I would be doing, where we have to solve a writing Q sharp code, and then this exercise will be presented with a placeholder code, and you will have to fill in the correct solution. Okay, so the input is 0, and we have to apply the X gate to the qubit. X gate is how we are passing through, or we are making sure that we pass this query, and we change the state of bit from 0 to 1, and that's what we are doing. So we are flipping the side of the coin and making it 0 to 1. As I said, now you might ask why, like it's in qubits, it's actually not 0 or 1, it's actually 0 and 1 both at the same time. So understand what I just said. Yes, it is 0 and 1 at the same time, but it doesn't go like this, 0 and 1. It's actually a little in the between. So it's more either on the 0 side or more on the 1 side of it. So it's like that. Okay. But we'll clarify it a little more in future, and why we do this, and what do you mean by X gate? X gate is is a processing through which I'm converting the 0 to 1. So what I do in the processing operation, so that's an operation that I'm performing. So namespace I've kept kata, and then the operation it's flip bit, which means I'm flipping the bit, and I'm making the q that's qubit unit is adjusted plus ctrl control, and then I make the X to Q. Okay, and when I do this, I just uncomment this particular section, and I hit run, and I will get the message that the solution is correct. Okay, so what I did is I just changed this Q, this Q to adjusted this Q from going to 0 to actually 1, something like that. But it was 1 and I made it 0, something like that. I made it go more or inclined towards the other, but it's not completely 0, it's not completely 1. It's more inclined towards 1. That's what the whole thing is. Okay, let's read about it. Let's have an overview of what the overview says. This kata introduces you to one of the core concepts in quantum computing, the qubits, and its representation in mathematical notion and in the Q-sharp code. So this kata covers the following topic: the concept of qubits, superposition, vector representation of qubit, direct notation for single qubit state, relative and global phase. Qubit data type is Q-sharp, and visualizing the quantum state using dumb machine. Okay, and what should you know is complex algorithm and linear algebra. This is what you should know, you should be aware of. If you are not very good with complex arithmetic, then this is not a very good thing for you to go. So I mark this complete. We go next. So the concept of qubit, the basic building blocks of classic computers is bit, a single memory cell that is either in the state of 0 or state 1. Similarly, the basic building blocks of quantum computer is quantum bits or qubits. Like the classical bit, the qubit can be in the state 0 or in the 1. Unlike the classical bit, however, the qubit isn't limited to just 2 states. It can also be combination of or superposition of these 2 states. So it can be both, like 0 and 1 at the same time, kind of thing. Common misconception about quantum computing is that it's a bit is always in the state of 0 or 1 or 0. We just don't know which one until we measure it. This is not the case. The qubit is in a superposition. It is in a linear position of state 0 and 1. When a qubit is measured, it is forced to collapse into one state or the other, which means once we read it, it's actually in this state of 0 and 1. But once we read it, it either becomes 0 or 1. It doesn't stay both. It just shows 1. That's what it says. In other words, measuring a qubit is irreversible. Once I see it as 1, it will remain 1. It won't go back to 0. It's irreversible process that changes its initial state. Okay. Matrix representation, if you want to understand, is the state of qubit is represented by a complex vector of size 2, that is alpha and beta. This is alpha and beta. Here alpha and beta are complex numbers. Alpha represent how close the qubit is to state 0, which I said, like alpha is like more towards 0, and beta represent how close it's towards a state 1. So let's say up is 0 and below is 1. So if it's more towards up, it's alpha. If it's more towards below, it's beta. Okay. This vector is normalized alpha square plus beta square is equal to 1. Okay. Alpha and beta are known in the probability amplitudes of the state 0 and 1. So basic states, qubit in 0 would be represented by the following vector: 1 upon 0. Likewise, a qubit in state 1 would be represented by the vector 0 upon 1. Okay, note that you can use scalar manipulation and vector addition to express any qubit state, alpha or beta, as a sum of these two vectors with certain weight x, alpha and beta, known as a linear combination. So alpha on beta is equal to alpha on 0 plus 0 on beta is equal to alpha 1 upon 0 plus beta 0 upon 1. Okay. Because of this, the qubit state 0 and 1 are known as basic states. These two vectors have two properties. They are normalized. They are orthogonal to each other. So this is a normal state. This is a normalized state where it's 1, 1, 0, 0 at the bottom, 0, 0 at the top, 1, 1 at the bottom, and it becomes 1. Orthogonal is other state, which is 1, 0 or 0, 1, 0, 1 or 1, 0, and it becomes 0. Okay, as a reminder, W, V or V is the inner product of W and V and W. Okay, this means that these vectors forms are orthonormal bases. The basics of 1 on 0 and 0 on 1 is called computational basics, also known as chronicle basis. There exists other orthonomical bases, for example, hammered basis formed by the vector 1 upon root 2, 1 upon root 2 and 1 upon root 2 minus 1 upon root 2. Okay. You can check these vectors are normalized and orthogonal to each other. Any qubit state can be expressed as a linear combination of these vectors. Okay, so alpha beta is equal to alpha plus beta upon root 2 into 1 root 2 and 1 upon root 2 plus alpha minus beta upon root 2 is 1 upon root 2 minus 1 upon root 2. This hammered basis is widely used in quantum computing, for example in BB84 quantum key distribution protocol. Okay, this is one of the protocol that if you want to read more about this protocol, you can always click on this link. So I've tried to cover some very basics in starting of it. I will cover the direct notion and the relative, global and other things in the upcoming videos. Happy reading. Have a great day ahead. Bye.